Welcome to my video course on mastering ERTMS, ECTS signaling systems. Today, we're going to deconstruct the digital brains behind modern railway infrastructure, specifically focusing on the architecture and real-world application of ETCS Level 1.
It's great to have you here for this explainer. We've got a lot of fascinating ground to cover today on how these systems actually interact out in the real world to keep trains moving safely and efficiently. So, here is our roadmap for today's session. We're going to start with the fundamentals of Level 1. Then we'll dive into fixed block operations, zoom right down into the hardware with Eurobalises and LEUs, and finally wrap up with the strategic power of using Level 1 as an infrastructure overlay. Let's get right into it.
Section 1. Intro to ETCS Level 1 and cab signaling fundamentals.
Okay, so ETCS Level 1 is honestly both a massive leap forward and a really brilliant engineering compromise. At its core, we're talking about a spot or semi-spot automatic train protection and control system. But what does that actually mean for the folks running the trains? Well, it means we're bringing interoperable cab signaling directly to the driver's dashboard. In the past, a driver had to constantly look out the window, searching for physical traffic lights along the side of the track. With Level 1, those crucial commands are moved right inside the cabin. But, and this is key, it still fundamentally relies on intermittent spot transmission of data instead of a continuous radio link. Because of this spot transmission, the onboard computer has to take the data it gets at very specific points and continuously calculate the maximum safe speed and dynamic braking curves until it hits that next data point.
Moving on to Section 2, the fixed block operation and retaining traditional track systems.
To really understand how this works in practice, we need to talk about fixed block operation. Here's the crucial takeaway for Level 1. It absolutely does not require a blank slate. It's a cab signaling system that is typically superimposed right on top of existing infrastructure. We aren't tearing up the old railway. Instead, we're building a highly advanced digital intelligence layer directly over it. So your traditional lateral signals, those physical lights beside the track, and the legacy track release systems, they remain firmly in place.
Think about a basic DC track circuit. This is technology that was actually invented by Dr. William Robinson way back in 1872. You have insulated joints dividing the railway into varying block lengths. There's a power source, like a battery, at one end and a receiver or relay at the other. When a massive train enters this block, its metal wheels and axles create an electrical connection between the two running rails. This physical track function is known as wheel-to-rail shunting. It drops the relay and boom, the system detects the train's presence. In ETCS Level 1, these deeply traditional, very physical track circuits just keep right on functioning beneath our new digital overlay. Because of this specific architecture, the track's traditional safety mechanisms are completely preserved. The fixed lateral signals stay exactly where they are. National signaling rules, they continue to apply just as they always have. Those century-old track circuits keep doing the vital job of train integrity supervision and track release detection. ETCS Level 1 basically acts as an advanced monitor in tandem with all this. It picks up the existing signal aspects and safely feeds them right into the modern cab.
Section 3. Eurobalises and route data, the spot transmission beacons.
Let's shift our focus down to the micro-level hardware components making all this possible. Meet the Eurobase. These are essentially the critical digital milestones of the ETCS system. They're radio beacons installed at fixed, specific points right in the center of the track. And remember, because Level 1 is a spot transmission system, the train absolutely has to travel directly over one of these Eurobases to get its next set of instructions, like movement authorities and route data.
The way they actually talk to the train is genuinely fascinating. It's called the air-gap interface. So the Eurobalise sitting out there on the track doesn't actually need its own constant power supply to broadcast. Instead, as the train passes overhead, the train's onboard unit projects a telepowering signal downward. This quick burst of energy physically powers the passive Eurobalise just long enough for it to wake up and fire its data telegram back upward to the train's antenna. It is a brilliantly elegant, completely self-contained communication loop.
So what's actually inside that data telegram shooting up into the train? Most importantly, it contains movement authorities, or MAs. Think of these as digital permission slips that allow the train to cross one or more block sections. It also transmits really precise route data, things like static speed profiles and track gradients. The train-borne computer instantly processes the spot data. It continuously monitors the maximum permissible speed and updates the train's dynamic braking curves. This ensures that even if a driver makes a mistake, the system will step in and safely bring the train to a halt before the end of its authorized movement.
Section 4. the Lineside Electronics Unit, or LEU, which serves as the safe interface. Now you might be wondering, how does a physical red light on the side of the track turn into a digital data telegram inside a Eurobalise? That brings us to the LEU. The Lineside Electronics Unit acts as the crucial translator between the old world and the new. It sits right between the legacy trackside signals, or the central interlocking, and the switchable Eurobalises on the track. It watches what the physical signals are doing and then encodes that exact behavior into a specific digital telegram for the train. Let's trace this data flow step by step. Imagine a trackside signal turns red because a block ahead is occupied. Instantly, the LEU, which is wired directly into that signal, interprets the interlocking data. It selects the corresponding stop command telegram and fires it down the cable to the switchable Eurobalise lying on the track. Then, when the next train passes over, it powers the balise and receives that exact braking command. We've just seamlessly turned a mechanical signal into a digital brake command. Pretty amazing, right?
Section 5. The power of overlay. Bridging legacy and interoperability.
To wrap up our architectural deconstruction, let's zoom back out and look at the strategic application of everything we've talked about. Look, railway infrastructure is incredibly expensive. If modernizing a network required a complete rip and replace of all the legacy tracks, relays, and signals, interoperability would be financially impossible for most operators. And that is the true brilliance of the ETCS Level 1 overlay. Instead of ripping out the old infrastructure, Level 1 acts kind of like a smart wearable for the track. It just fits perfectly over what is already there.
To sum this up, the overlay approach is just a highly practical, elegant engineering solution. It can be installed without removing existing national systems, it provides an immediate transition toward modern, interoperable cab signaling, and it utilizes the existing track circuits and mechanical signals we discussed earlier. This makes it a highly cost-effective migration step, moving railways into the digital age without bankrupting the operators in the process.
Now, before we wrap up this explainer, I want to leave you with a thought-provoking question to set up our next module. We know that ETCS Level 1 relies on intermittent spot transmission every time a train passes over a Eurobalise. But what happens if the situation ahead changes while the train is in between two balises? If ETCS Level 1 relies on spot transmission, how do you think Level 2 builds upon this foundation with continuous radio communication? Think about how that continuous link might completely change the role of those physical signals and the Eurobalises we just learned about.